In this video, we're going to be talking about ISO standard 230 part 2 regarding accuracy and repeatability of positioning of CNC machines, and we're going to clarify a common misconception about accuracy and repeatability. Welcome to Manufacturing Engineering. So, why are accuracy and repeatability of positioning so important? Well, they're pretty much the only two values a machine manufacturer will display publicly that express how quote-unquote accurate a machine is. There are obviously more types of machine accuracy than just positioning accuracy and repeatability. For the full breakdown, you can check out John Miller's video Machine Accuracy on his YouTube channel Way of the Mill. And now, let's get started with the ISO standard. To get started, all you need is a browser and some kind of spreadsheet software like Microsoft Excel, Apple Numbers, or Google Sheets. We're going to start with the browser and type into the search bar iso.org. This is going to take us to the official website of the International Standardization Organization. Now on that website, open the search bar again and search for 230-2. In this video, we'll be using the 2014 revision of the standard. Click on the preview button and you will see the table of contents. We're mainly going to focus on Chapter 3, since every other chapter containing information about selection of target position, test conditions, and test programs is hidden behind the paywall. As stated in Chapter 1, all the methods in this standard apply equally to linear and rotary axes. Now let's start with point 3.1, and that is axis travel. You will see this called out on most machine specs for X, Y, and Z dimensions, and if present, either A or B and C dimensions. Part of that axis travel is the measurement travel, which is point 3.2. It's smaller than the full axis travel because all measuring positions must be approached from two directions called positive and negative direction. Point 3.3 is the functional point, so the point at which the measurement takes place. And the best place for that is the center point of the cutting tool, since this is the location where we want to get accurate cuts after compensation for the cutting tool geometry. Point 3.4 defines the target position, and point 3.5 defines the actual position. And now we're going to use Excel for visualization. Here you can see the first 4 rows of the table, which we're going to use to calculate accuracy and repeatability. The first row is our subscript for the target position I, and the second row is the subscript for the actual position J. Row 3 shows the programmed value for the target position, in this case 25 mm for target position 1 and 50 mm for target position 2. Row 4 shows the value for every performed measurement at a target position. This represents the actual position to which the axis traveled. As you can see, there is a difference between the actual position and the target position, and that leads us to point 3.6, the positioning deviation. It can be calculated by subtracting the target position from the actual position. The positioning deviation not only shows that there is a difference between each measurement for a given position, it also shows that there is a difference between the measurements from the positive direction marked green and the negative direction marked red. As described in points 3.7 and 3.8, columns C, D, and E can be referred to as unidirectional series of measurements, while columns C, D, E, F, G, and H can be referred to as bidirectional series of measurements. Points 3.9 to 3.12 describe terms that are used to express uncertainty for the measurements. At first we have the standard uncertainty, expressed as a standard deviation, and the combined standard uncertainty. After that we have the expanded uncertainty, and finally the coverage factor. If you don't know what a standard deviation is, check out Jeremy Blitz-Jones' video on standard deviation. To calculate the standard deviation, we need the arithmetic means for all unidirectional deviations, so we'll get 2 means for a target position. In our example, the 2 unidirectional means are displayed in rows 6 and 7, named mean xi POS and mean xi NEG, respectively. POS indicating the positive and NEG indicating the negative approach direction. In the next step, we'll calculate the arithmetic mean for the bidirectional positioning deviation. This can be done by adding the two unidirectional means together and then dividing by 2. After that, we can continue with point 3.15, which is the reversal error at a position. It can be calculated by subtracting the mean negative unidirectional deviation from the mean positive unidirectional deviation. To get the reversal error of an axis, you simply take the maximum of all the reversal errors at all positions. The next point is 3.17, which is the arithmetic mean for all reversal errors at all positions. And now we finally get to our standard deviation at point 318, described as the estimator for the unidirectional axis positioning repeatability at a position, which is a mouthful. It tells us how far the deviations are spread out from their mean. Since it's a unidirectional estimator, it has to be calculated for both positive and negative approach directions. We're going to combine the estimator with our coverage factor, in this case 2, by multiplying the estimator with 4, giving us the unidirectional positioning repeatability at a position. The coverage factor of 2 means that there is a 95% chance of a measurement being within plus or minus 2 standard deviations. Next up, we have the bidirectional positioning repeatability at a position. This is the maximum of 3 values: the positive positioning repeatability at a position, the negative positioning repeatability at a position, and the sum of the absolute value of the reversal error at a position and the positive and negative standard deviations multiplied by 2. Now we convert all the repeatabilities for a position into repeatabilities for an axis by simply taking their maximum value. We do that for both uni and bidirectional repeatability, and as you can see, we have the first value we were looking for at the start of this video. Point 3.22 is the bidirectional positioning repeatability of an axis, and if you take the max value from the x, y, and z axis, that is the value displayed on most machine specs. Now we only need to define the positioning accuracy of an axis. For that, we'll start with point 3.23, which is the unidirectional systematic positioning error of an axis. It's calculated by subtracting the minimum mean unidirectional deviation from the maximum mean unidirectional deviation. After that, we calculate the bidirectional systematic positioning error of an axis by taking the maximum value of all mean unidirectional deviations and subtracting the minimum of the same mean deviations. While point 3.23 and 3.24 are showing the difference between the extremes of all mean unidirectional deviations, point 3.25 shows the difference between extremes of mean bidirectional deviations. And now we have reached point 3.26 and 3.27, which are the unidirectional and the bidirectional positioning accuracy of an axis, the latter being the second value we were looking for at the start of this video. It is designated as capital A, and you can see it on most machine specs. This wraps up the explanation part of the video. Feel free to rewind to parts you didn't fully understand. Now, what's the misconception I talked about at the start of the video? If you've ever talked to a machinist about positioning accuracy, for example in the context of your company being in the process of buying a new machine, and you tell him that a specific machine has, for example, a repeatability of 5 micrometers, you might have heard the following interpretation. The machinist knows that the parts that are supposed to run on that machine have tolerances of plus minus 5 micrometers, so he will say that the machine is not accurate enough to reliably hold those tolerances. So is he right or is he wrong? Maybe, because as stated at the start of the video, a machine's accuracy involves more than just positioning accuracy and repeatability. Things like thermal stability, vibration dampening characteristics, and even the concrete on which the machine stands. So just referring to 2 values for the full description of a machine's accuracy is not sufficient. And with that, thanks for watching.